Yeah, thank you for the introduction. Good morning. Thanks again for coming here. I'm Matteo. I'm an assistant professor here at University of Milan, and I work on reinforcement learning. Today I will tell you about a recent interest of mine that are state representations based on the graph Laplacian. It's an old idea in reinforcement learning and maybe a bit out of fashion, but I think there are some things, some interesting things to understand and to develop still. So I will talk about this recent work that just got accepted at ICML. This is actually the master thesis of a student from Politecnico di Milano, Tommaso, co-supervised with Pier Riccardo, and also with Laura and Keue from UCL, who in this project were like our graph experts. Let's start with some motivation. So imagine that you want to navigate the Milan metro system, okay, to get to places. This is a very complex environment with a lot of information to process. And so what you need is some compact representation of this very complex environment. And then once you have access to this representation, you can more easily solve your tasks that would be going from your home to the university or from one university to the other. I don't know. Okay, what is good about this kind of representation is that it preserves the relationships between the states of this environment. The states are simplified, and you can imagine the stations are the states, but the topology of the environment is somehow preserved. What is not good about this representation, though, is that you need to explicitly memorize this graph. So the idea is to develop a kind of representation for reinforcement learning, so a state representation that preserves some of the topological features of the environment, but is also compact. And this is the idea of using the graph Laplacian for representations. Now let's take a step back and formalize our setting. So I'm considering a controlled Markov process. So it's a Markov decision process without the rewards. We have a set of states that you have to imagine to be very large. So you cannot store information for every single state separately. Set of actions and stochastic transitions between states, depending on the actions the agent plays. Let's say they're discrete, yes. Actually, they could be also continuous, but let's say they're discrete for simplicity. Just the state space is very large. And then you can, of course, define policies that are stochastic mappings from state to actions. And if you add a reward function, you get a Markov decision process. But for learning representations, imagine you don't have rewards. Later, you might be given a task in the form of a reward function, but you want to use your representation to solve possibly many different tasks within the same environment. We adopted the average reward formulation. The definitions are not very important here, but this row is the average reward that the agent gets, of course, once a task is given by playing some policy. So if you fix a task and a policy, then you can compute the average reward of an agent. And the value function v pi s measures how good a state, how valuable a state is under this policy. It's how much more reward you get by starting in this state compared to being just in random state. So the main goal of this is policy optimization, is finding a policy for a given task that has high average reward, but we will focus instead on policy evaluation. So given a task and a policy, we want to estimate the value function, the value of each state. This is the task we will focus on, and you have to build these estimates based on data you collect by interacting with the environment. And to do this, we will use state representations because the state space is too big. These often in reinforcement learning are given, but we want also to learn them from data. And we can learn them from reward-free data before being given a reward. We can see this as a form of unsupervised reinforcement learning or unsupervised pre-training. Then once we have learned these representations, which is just a mapping from states to a small set of features, D features, then we can use this representation to solve multiple tasks, okay? So you can spend maybe a lot of data just to build this representation, and then once you are given a reward function with a few data possibly, then you can estimate the value function using linear function approximation. So once the representation, the features are fixed, you just need to find the weights for the given task. But now let's look at a representation that that is related to the topology of the problem. What you see here is the graph corresponding to a navigation task that we will see better later. And what I want you to remember for now is that when I talk about graphs, the nodes of the graph correspond to states, and the edges correspond to transitions between states. Okay, what we can do is to build such a graph for a Markov chain. So we need transitions between states. And to do this, you need to fix a policy, okay? Because the transitions between states depend on the action. So only once you have fixed a policy, you can define this Markov chain and this graph of transitions among states. So let's call P pi. Later I will drop the pi and it will just be P, but this is the transition kernel of the Markov chain once you have fixed a specific policy. And I will call phi pi, or just phi, when it's clear from context, the stationary distribution of this Markov chain, which exists. Let's say it exists. We need some assumptions for this, but don't worry. Now we have a Markov chain, so we have a state graph, which is a directed and weighted graph. The weights are the probabilities of going from one state to the other, of course. And the weight matrix is our P, our transition matrix. Now, let's first assume that P is symmetric. This is a simplification, of course, that we will drop later. But it's very common in this literature on graph representations for reinforcement learning. Then you can define the Laplacian of the graph. Now we have a graph that is weighted but undirected. You can define the Laplacian like this. It's just identity minus P. And what is interesting is the spectrum of the Laplacian. If you look at the eigenvalues of the Laplacian, they're very interesting. So, okay, the first eigenvalue is always 0. But the second, the smallest eigenvalue is more interesting. It's always called the algebraic connectivity because it carries a lot of information about the connectivity of the graph. For example, if the second smallest eigenvalue, well, if the second eigenvalue is 0, the graph is disconnected. And if you have a higher multiplicity of the 0 eigenvalue, it means you have more components. We will consider graphs that are connected. So we just have the first eigenvalue that is 0, and then the other ones are non-zero. And this lambda 2, the second eigenvalue, is also related to other notions of connectivity. I will not go into details, but then if you go up and you consider larger and larger eigenvalues, what you can see is that smaller eigenvalues are associated with smoother state functions. So if you select the first eigenvectors or eigenfunctions, because they are functions of the state associated with the smallest eigenvalues, these are sort of the most important features you can extract. And this was the idea of proto-value functions, which was introduced in this seminal paper by Madevan and Maggioni. So you select the first k eigenvalues of the graph Laplacian, you take the corresponding k eigenfunctions, and these are your features that you use to approximate value functions. And then the point of this is that you can get a good approximation of the value function for a given task. And what you have to do is just to recover the weights, for example, doing least squares. How good? This is our main contribution. Like understanding the approximation error of this is our main contribution. Again, what is good about this specific representation? There are many representations in reinforcement learning. What is good about this one is that also empirically you can see it can capture some interesting topological features of the problem, like highlighting bottlenecks or identifying parts of the environment that are more connected and so on. What is not good about this representation is that it is ultimately tied to the policy that you use, because we have fixed the policy just to build this graph. And so the policy you use in the unsupervised pre-training in the representation learning phase determines the representation that you're building. So if you want to use this to evaluate other policies or to do policy optimization, you might have some problems.
So if I remember correctly, Laplacian eigenbases are more like Fourier function defined on the base of the vector.
Yes, basically, yes. That's correct. Okay, more recently, so another thing that is not good is that in principle we have to build a model of the environment, right? Apparently it is inherently model-based. You need to build a model of the environment to build this graph and then compute the Laplacian and extract the most important features. Now, more recently, people have developed methods to do this in a model-free way, using the graph drawing objective. I will not go into the details of how this algorithm works, but essentially you can learn the features directly from interaction data, so unsupervised reinforcement learning, model-free, so without building an explicit model of the state graph. And usually these state basis functions are parameterized by neural networks. So there are practical implementations of this. Now, when the features are learned in this way, I will put a hat on the features themselves. Okay, so when you build then a linear value function approximator, you have two sources of approximation. One is because you are using only k of the eigenvectors, which The total number is the number of states, of course. We are just using a small number k. The other source of error is that these are not the true eigenvectors. They've been estimated from data themselves using this graph drawing objective. Okay. Now we have to deal with the symmetry business, because if you think about it, it's not. Yeah. Realizability. You can recover the value function. Yeah. Yeah. It's a function defined on the nodes of the graph, so you can completely recover it. Yeah. Okay, symmetry is not good actually, because think of the simplest navigation task, a grid word, okay? And the agent can move in this grid, and tasks are like, you have to reach this goal here, starting from here, okay? Now, this is one of the most symmetric problems I can think of, because all actions are reversible. And it is actually, the transitions are actually symmetric if you consider a uniform policy, a policy that plays random actions, which is the one that is mostly used in works about this kind of representations. But as soon as you consider policy, like meaningful policies, for example, that have a preference for going towards this area of the environment, then the symmetry is broken. So what do you do? There are symmetrized Laplacians. We consider this one proposed by Wu et al. This is not the original expression. In the paper, we have a long discussion about the original expression was correct, but led to a lot of confusion in subsequent works. So this is the expression we suggest to use. The important thing, and this is going to be a common theme, is that everything is weighted by the stationary distribution of the policy that we are considering. So this phi is a matrix that has the stationary distribution on the diagonal. And if we construct the Laplacian like this, it's going to be self-adjoint, well, phi self-adjoint, which is this. So it's like a symmetric, but in this space where that is weighted by where states are weighted by the stationary distribution. Finally, our main contribution is characterizing the approximation error. So of course, you may expect that if you increase the number of eigenvectors you use, the approximation error goes down. This is obvious. But we can say something more interesting also. These are our assumptions for this analysis, which are just like considering the algorithms we are using in the unsupervised pre-training phase, and then in solving the downstream task, the policy evaluation task. So the first one is an assumption on how we estimate our features. It seems complicated, but actually it matches the objective of the graph drawing algorithm that I was talking about. Essentially, this graph drawing objective is able to recover the eigenvalues of the true Laplacian and is able to recover features that are orthonormal. But again, everything is always weighted by the stationary distribution. So this is let's say a reasonable assumption if you are using this graph drawing objective to estimate your features, and epsilon will be how good this reconstruction is. So this epsilon captures the residual error of this representation learning phase. And then once you have the features, we are assuming a least squared oracle. So once you're given the features, you can perfectly recover the weights for the given task. This, of course, is a simplification, but it allows us to focus on the representation error introduced by our representation. Again, always weighted by the stationary distribution. The regression is also weighted by the stationary distribution, which just means that all the data you collect are under the policy that you are considering. And now we can decompose the value function approximation error. Let's do this first. So if you are given access to the true first k eigenfunctions, then and you build a linear value function approximator using the first k eigenfunctions, then your error, again measured with a norm that is weighted by the stationary distribution, it has this upper bound. So there is an obvious part in this upper bound. It goes down with lambda k plus 1, which is the first eigenvalue that you discard. So if you include more features, the error decreases. But also the lambda 2 ended up in this upper bound, which is the algebraic connectivity. So the intuition is that this representation is going to be more accurate for a graph that is more connected. This was our interpretation. Of course, it's an upper bound. Upper bounds can be misleading, but we will see that in practice, we actually observe this decrease when the graph connectivity increases. Okay, then this was with exact features. If the features are, if the features are estimated themselves using the graph drawing objective, then we can bound the difference between the two projectors, the one to the true eigen basis and the one to the estimated one. And this is controlled by the error of the graph drawing objective algorithm, which is good. So this means this source of error can be controlled in practice also. Putting things together, we get the sum of the two. We get the an upper bound on the approximation error of our value function. The take-home message is that the feature estimation error is controlled by the graph drawing objective, so by our representation learning algorithm, and the truncation error improves with the connectivity of the graph. So to see this in practice, we built these grid words with changing amount of walls. So you can have almost no walls and a very connected state graph. You can have a sort of labyrinth where the graph is less connected and more interesting structures emerge. And first of all, we check that the lambda 2, the algebraic connectivity correctly captures our intuitive notion of connectivity, which is the case. So here is smaller, here is larger. So more connected graph, larger lambda 2. And then we observe that the quality of our value function approximation improves as the graph gets more connected. So here you have lambda 2, and here you have the error, the value function, the error on the value function. Okay, there are still many questions. What we want to study now is so again, we want to free this representation from being tied to a specific policy. So the first question is, what is a good policy to use in the representation learning phase? Because typically the uniform policy is used. but it's not necessarily the one that makes the problem easier. Our intuition now is that we need something that induces a more connected state graph. And the next question would be how then the representation generalizes to different policies. So you learn under a policy, can you evaluate other policies? And this also depends on the choice of the policy that you use to collect data. And if we can do this, then maybe we can say something about policy optimization. So, but can you fix the representation and then consider a sequence of improving policies and maybe finding the optimal policy? That's all.
Okay, thank you. Yeah, I have a question. Okay. So, okay, I started my reinforcement learning research 20 years ago. And the first work was like extension of Mahadevan's and Maccioni's paper. And we found that, okay, that method worked quite well in terms of the like global approximation of the value function. Yeah. So, but on the other hand, if we want to update the policy, not the global structure, but local structure is more important because we care surrounding states and surrounding value functions. And actually, we define the Gaussian kernel on the graph. Then it worked much better in practice. So did you observe similar phenomenon here?
So, so what do you mean by local structure?
Like if I'm on this state,
yeah,
you want to know the value of neighboring states, either like value.
Okay. No, I see. We didn't really consider this because we are always measuring the value function error on the whole state space. Yeah. So we didn't go into this, but it would be super important for this part. Yeah. Like if you're doing policy improvement, then I guess it's super important. Yeah. And right, people have worked on hierarchical versions of this, right, where you for each room. Right. I have seen those papers. You use this information on the graph to split the environment in many parts. Yeah.
And on the other hand, recent deep learning guys learn representations of the state itself, not the value function basis functions.
Yeah.
State representation themselves. Do you also consider similar extension?
What do you mean the state itself? Because we do have state. We do have state features.
Deep learning and learn features.
Well,
state embedding.
This is essentially what the graph drawing objective is doing, right? It's.
You still have S directly, and this phi S is here. Okay.
Yeah.
Right. Okay. In terms of value function, right? But then, can you use the same like phi hat S for learning the policy and doing everything?
I don't see why not. Yeah.
Maybe then. But this is still the first step. So
yeah.
Understood. Thank you.
Okay. Thank you.
Other questions?
Good morning, everyone. I'm Gianmarco Genati. I'm a postdoc in Politecnico di Milano. And today I'm going to present the mixing of two works I presented in the last two calls about Untitled Bandits, which are joint works with Alberto Maria Metelli and Nicola Gatti. So I'll start by setting up some ground notation on K-arm bandits, stochastic K-arm bandits. We say that an instance is a collection of K probability distributions, okay? And at each round, T, over a time horizon large T, a learner chooses an action high T among the K available, and then it receives a reward. The reward is a stochastic sample from the distribution associated to the action, okay? And the overall goal is to minimize the cumulative regret, okay, which is defined in this way, which is the discrepancy gap with respect to the best possible decision maker. Okay, in the stochastic case, the best possible decision maker, of course, is the one always choosing the action with the largest average reward. The setting we are interested in today is a, let's say, generalization of the standard setting that is studied, which is the heavy-tailed setting, okay? In the heavy-tailed setting, the assumption that we make on the probability distribution generating the rewards is that the 1 plus epsilon order moment is bounded by constant u. In general, in most of the literature on stochastic error bandits, the distributions are assumed to have bounded support or to be sub-Gaussian. So this assumption is weaker and models a broader class of problems, okay? Note that epsilon may be smaller than 1, okay? And this means that the variance may be infinite. So the rewards may have infinite variance, which is crucial for the characterizations on this problem. There are some neighboring settings with alternative definitions or that have like shared techniques and shared algorithms. There is bandits with Pareto reward distributions, problems with reward corruption, evitable reinforcement learning, of course, and risk-sensitive bandits. Okay, these settings are neighboring, but there are some crucial differences. So there's a seminal paper from 2013 that introduced this problem, okay, and provided the first characterizations. In particular, in the papers are provided two lower bounds on the regret that can be attained by any algorithm in this setting. One is a worst case lower bound on the regret, and the other one is gap dependent because it depends on specific parameters of the instances, which are the suboptimality gap between the best action and all the other actions I, okay? This is quite standard in bandit literature. And of course, in the paper, algorithms matching these two lower bounds are presented. Okay, so there are already algorithms optimal in this sense. What's important to notice here is that the two quantities, epsilon and u, which are the quantities that characterize the tails of the distribution generating the rewards, heavily affect these two bounds. Okay, u and epsilon are really important in the rate that an algorithm can achieve. So what's the catch? The catch is that basically most of the existing literature assume that these two parameters, u and epsilon, are known to the learner, are known to the algorithm. In fact, these two quantities are usually unknown in practice, okay? Because they are tail parameters, and also when epsilon is less than 1, they are quite hard to estimate, if not impossible, with a reasonable rate, okay? So that's why we shift our focus on heavy-tailed bandits on the problem of adaptation in heavy-tailed bandits. So to provide algorithms and to characterize how hard is this problem when these two quantities are unknown to the learner, okay? So when both are known, as I said, both words optimality has been achieved in the sense that both the gap dependent and the worst case regret lower bounds have been matched by some algorithms, okay? And in a recent work that we presented at COLT, we proved that if you do not know neither epsilon nor u, okay, and no additional assumption is made on the environment, then the rate that I presented before, the one from the first paper on heavy-tailed bandits, cannot be achieved anymore. And we have two lower bounds, okay, that shows that in the first case, when u is unknown, so epsilon may be known, but u is unknown, then the optimal rate cannot be matched anymore in the dependence on u, okay? And when epsilon is unknown, so either if u is unknown or epsilon is unknown, the bounds cannot be obtained anymore. And in the case of epsilon, this is particularly problematic because also the dependence on t increases. So what we did in the first place was to search for an assumption which is reasonable to add and which can allow us to obtain optimal rates for regret minimization heavy-tailed bandits without knowing u or epsilon or any information related to them, such as an upper bound, okay? And we found an assumption introduced by Wang et al. For the first time called truncated non-negativity, okay? In truncated non-negativity, which has been introduced for loss bandits, so bandits in which you observe a loss instead of a reward, okay? We assume that the tails of the distribution, if we take the expectation on the tails for every possible threshold for which I define the tails, which is m, then the expectation is non-negative, okay? To the best of our knowledge, and by deeply searching in the related literature, this is the only assumption that is independent on u or epsilon, because there are other assumptions, but they depend on the values of u and epsilon, and we wanted to avoid that. Of course, we are in a reward bandit, so we had to translate this assumption in the reward setting. So we basically flip the sign, and we use the truncated non-positivity assumption instead of non-negativity. It's a really similar assumption. And I mean, for reward bandits, we needed to do this switch of sign. Note that even if we add this assumption to the setting, when u and epsilon are known, then the worst case lower bound is preserved. So this assumption doesn't make the problem easier, okay? So this is a, let's say, short literature review on heavy-tailed bandits. There are many papers, I mean, I omitted many of them, but there are many papers where epsilon and u are both known, so the standard setting, like the very first paper. And in general, when both epsilon and u are known, both the distance dependent and the worst case bound can be matched, okay? Then there are a couple of works in which u is unknown, but epsilon is known, okay? In this sort of hybrid setting, actually, the two presented algorithms don't match both rates, okay? Not one of them, actually. And then there is this recent literature in which epsilon and u are both assumed to be unknown, okay? There is like a zoo of assumptions that one can make to compensate for the fact that these two parameters are unknown. We decided to go with the truncated non-positivity, so being coherent with the works from Wang. There are two of them. And this is our work. To the best of our knowledge, this is the only work in which we are able, thanks to this assumption, to match both rates, both distance-dependent one and the worst-case one, without knowing neither epsilon or u. So I'll quickly go into the algorithm that we used to match these two lower bounds by avoiding any knowledge on epsilon or u. Neither an upper bound on epsilon or u is known or a lower bound, so we do not even know the range. Okay, so just a premise. UCB-like strategies don't work in heavy-tailed bandits, at least the standard ones. Okay, that's because empirical mean has a slow concentration rate for this kind of distributions. Okay, so we have to forget using standard empirical mean, but still UCB-like strategies can be used if the estimator is changed, and we move to robust UCB, which uses a robust mean estimator instead of the empirical mean. In our case, we opted for the trimmed empirical mean. The trimmed empirical mean presumes the knowledge of a threshold M, which is used at any round to clip the observation, to trim the observations. Okay. The problem is that if one wants to obtain tight regret rates with robust UCB with trimmed mean, one has to set the clipping threshold to a specific value that depends on both u and epsilon, which in our case are unknown. So it's not possible for us to directly set the clipping threshold in this way. We need a way to estimate a clipping threshold in a way that is bounded, upper bounded by a quantity similar to this one, but without using epsilon or u. Luckily, it is possible to show that the solution to this random equation is actually upper bounded by what we need. So basically, this result can be proved by characterizing the random zeros of that equation right there. And those random zeros can be shown to be upper bounded in high probability with a form that depends on u and epsilon, even though u and epsilon do not appear in this equation. This equation is fully data-driven, okay? And this allows us to use robust UCB without knowing epsilon and u. And so, in the end, to obtain tight rates. Okay? So, in fact, this algorithm is the only one so far having tight regret rates in both cases without knowing epsilon or u by using the truncated non-positivity assumption. Interestingly, I recently discovered that this algorithm is also tight in the case of Pareto reward distributions, even though Pareto reward distributions do not satisfy our assumption. So this is, I'm still wondering why, but I recently discovered this fact. So let me quickly go over some research questions, which are on which I'm focusing over the last couple of years. So the first one is, okay, we know that if you do not know epsilon and u, you can add an assumption and still obtain the optimal rates, the tight rates as if epsilon and u are known. But what is actually the best possible rate that one can obtain if epsilon and u are unknown and no additional assumption is added? So this is more of a problem characterization question. Then, of course, the follow-up question is, okay, assume that I'm able to characterize such complexity, then what is the algorithm that actually can achieve the best possible performance without any knowledge and without any assumption? And finally, if I opt to choose an assumption to subside the necessity of knowing these two parameters, then what is the best possible assumption? Is there a way to characterize in some way a good assumption, a weakest assumption among them all that allows me to obtain the optimal rate without any knowledge on these two parameters? So I partially answered the first question, but it's I mean it's not a published work or any. It's just some calculations. I draw inspiration from a work from Adige and Stolz, a recent work from Adige and Stolz, in which they focus on adaptivity to the range in stochastic bandits, in which the reward distributions have their probability bounded in some support. The type of result that they can obtain is quite peculiar because they have a relationship between the instance-dependent rate and the worst-case rate. And they show that the product of the two rates must be at least t, linear, okay? Keep in mind that adaptation to the range in stochastic bandits and to sub-Gaussian parameters is also an open problem in some sense. And what we did is to adapt this procedure and obtain a similar bound for heavy-tail bandits. In heavy-tail bandits, the relationship between the instance-dependent rate and the worst-case rate is a little bit more involved. Here we are in the case when u is unknown, but epsilon is known. And what's fun about about this rate right here is that if we set epsilon to 1, so the variance is finite, then the worst-case rate is lower bounded by t to the 2/3. One can argue that this can be matched by explore then commit, but remember that we are also interested in the dependencies in u and epsilon, not only in t. So this is all. Thank you all for your attention.
Thank you very much. Any question?
Thank you for wonderful presentation. My question is about the case of armwise parameter, like what we can get when the epsilon and the parameter are different for each arm. Like, for example, there are limited number of arms have heavy tail, but the other arm has a sub-Gaussian. Can we get improved upper bound?
Okay, yes, I think that this is possible because what I didn't say is that the truncated non-positive assumption is only required for the best action. So in the case, for example, in which the best action is sub-Gaussian and all the other actions are heavy-tailed, I think that we can definitely improve the rates because most of the analysis is mainly concerned with avoid underestimating the best action. And avoid underestimating the best action is only difficult if the best action is heavy-tailed in this setting. So I think that it's possible to improve the rate.
do you have some lower bound for such scenario?
Actually, no. I look sometimes on some stochastic scenarios in which all actions are detailed with different parameters, and see, for example, if you can have a dependence on the most benign parameters among all of the actions, but still I've never found a lower bound. I mean, I haven't even tried, so I mean, for sure this could be.
Thank you.
So yeah, but the unknown range problem, you cannot solve it, right? There are lower bounds to get the adaptive range adaptive bounds. Yeah, well, there's also this other work by Latimore and Gershinovitz that tells you that basically you have this, the range is changing according to a random process and within a bounded support.
And there, if I do remember correctly, it's the one in which the regret bounds to the maximum.
Exactly, the regret bound cannot scale with the range. That's the thing. So this is a different one. This is a different way of, okay.
Yeah, it's, I mean, I do not know that paper in depth. Yeah, I always forget Mike. I do not know that rate in depth. I think there are for sure some relationships. Maybe I should have a look in the next days. However, I think that if the rate is unknown but fixed, it's still possible to have in some sense sublinear regret. If I mean, if the range is fixed, if the range is dynamic,
yeah, you can have definitely sublinear regret, but it cannot depend on the range. But that's yeah. This tells you that the product is linear, so it's a different thing. Another idea, another thing, curiosity more is: do you have a best arm identification bounds for the heavy-tailed case? Or it's only regret?
There exists a paper on best arm identification for heavy tail with heavy tail random variables. It exists. It's a paper I think from 5 or 6 years ago. I don't remember the authors, but I do remember at some point posing myself the question and saying, "Oh, let's see if someone made pure exploration." But I think it already exists.
So I have a question as an informed outsider. So like to me, you two are working on quite the same problem. But is it really correct? You are working on the same problem in the same framework, but just you didn't meet each other previously? Or do you have any difference in, I don't know, philosophy or mathematical background or whatever that you can't collaborate easily? What do you think?
You mean?
I mean, if they are working on the same problem, same mathematics, just they didn't meet each other, then they can discuss now and find a common topic. So that can be done immediately. Or is there some philosophical difference between two groups and or mathematical differences? Yeah, that's great. I mean, topics are quite.
There's a bandit variation for every word in the dictionary. So basically, I think that everyone is kind of doing its own type of bandits. There's one type of bandit for research and bandit theory. So it's.
Okay, great. Thank you very much for the great presentation.
All right. So my name is Davide Chicco. I'm a researcher at Università di Milano Bicocca. And today I'm going to talk about a study that I recently published, in which I worked with my colleagues Simone Melzi and Francesca Gasparini from our department, and also with Giuseppe Jurman from Fondazione Bruno Kessler. And it's entitled The Advantages of Our Proposed Saturn Coefficient over Continuity and Trustworthiness for MAP Dimensionality Reduction Evaluation. So first we will say something about dimensionality reduction, which is probably a topic that you already know, so be quite short on that. I will say something about UMAP and the measures that are currently used for assessing its results that are continuity and trustworthiness. I will present our Saturn coefficient, so the metric that we propose to assess the results of a UMAP dimensionality reduction results and present some results and discussion and conclusions. Here, I won't show that much mathematics, so I hope it's going to be clear anyway. It's going to be more practical. So just to refresh the concepts that we see is that we are talking about dimensionality reduction, which is mathematical set of methods that can help reducing data sets that are in higher dimensionalities, so in a lot of dimensions, even 100, 1000, whatever. And you reduce it to a lower dimensionality. This usually it's 2, so you can see it. And but you want to do this dimensionality reduction by preserving the local structure and the global structure of the original data set. Otherwise, you're not going to analyze it. You're not going to be able to use it properly. So this is an example taken from Geeks for Geeks. You have 3-dimensional data sets that then is reduced into a 2-dimensional data set in the center, and eventually is reduced in 1-dimensional data set. So that's the simplest possible case. In reality, things are way more complicated, but we will see. And so UMAP is a method for dimensionality reduction. It was introduced, I think, 10, 15 years ago, based on concept from manifold learning and topology, models the data as the high-dimensional manifold, which is a mathematical space that locally resembles Euclidean space but can have more complex structures. And additionally, UMAP constructs a weighted graph representation of data using fuzzy simplicial sets. And some studies in the last 10 years or 15 years have shown that usually the reconstructions, the projections made by UMAP are better, more informative than TSNE. And if you are thinking about principal and component analysis PCA, that works only with the linear representation. So UMAP catches non-linear representations. Last step involves creating a neighborhood graph where each point is connected with nearest neighbors and the ways to reflect the distance between points. And then there is another step of the algorithm that preserves the structure of the high-dimensional data in the lower dimensional space by minimizing the differences between the original and projected data neighborhood structures. And this goal is achieved through a stochastic gradient descent optimization process. And this phases, as I said, how UMAP to represent nonlinear relationships between data in its dimensionality reduction results, while PCA, principal and component analysis, is not capable of doing so. Okay, so the problem is that when people do UMAP, when people use UMAP, especially in bioinformatics, in health informatics, and they need to assess the results, they just look at the plots. They just visually print the graphics, the images of the results, and they say, this is good, this is wrong, we are satisfied. And so, as you can imagine, this process is very subjective because one person can say it's a good result, another person can say it's a bad result, and so on. And anybody can see anything in their plots. So this is a famous study where UMAP was used for single cell-seq data in the bioinformatics framework. And these are the results that are presented in this paper, where they picked the groups of points that were represented by UMAP, and they were able to find some cell types and some sample types of the data set, but these colors were done manually. So you might think that was some kind of advanced annotation process. No, it's done manually. So they decided to print to color green those points, to color blue those other points, and so on. As you can imagine, this is a limitation of this approach because anybody can make a guess or can say something about it. And to assess the results of UMAP, scientists already proposed two metrics that are not, to be honest, they're not very used. One is continuity, that indicates which points, how much the points that are close together in a high dimensional space remain close together in a lower dimensional space after the application of UMAP. And trustworthiness, on the other hand, measures how well the local relationships are presented in embeddings. So high trustworthiness score indicates that 2 points are neighbors in the original dataset space. They are likely to remain neighbors in the UMAP reduced space. And the trustworthiness and continuity range from 0 to 1, where 1 is perfect and 0 is completely wrong. So we try to do something better than them, to propose something. We decided to, we proposed this solution that we call the Saturn coefficient, that is the metric that we propose for this goal, that can capture both the conservation of the local structure of the original dataset and the conservation of the global structure of the original dataset. And the Saturn coefficient is based on the distances between pairs of points before dimensionality reduction and after dimensionality reduction. So the basic idea is that if 2 points, if 2 rows are close together before UMAP, before applying UMAP, we ask, are they going to be close together after applying UMAP afterwards? If the answer is yes, our Saturn coefficient gets a higher value. If not, yeah, lower value. So if most of the points, most of the couples of points stay together after apply UMAP, we have a high value of UMAP, of the Saturn coefficient. So very simple. I don't have the mathematical formulas that you guys have, but way more simply, I wrote them. So you have a input matrix or table. You scale A by column on the matrix X, and you compute. We computed the triangular matrix of the distances between each pairs of rows of X, and we saved it in this dx triangular matrix variable. Then we apply a UMAP to X, and we save the result into the matrix U. And then we scale U, and we put it in the variable Y. And we, again, calculate the triangular matrix of the distances between pairs of rows of Y. And we put them into the dy variable. And then we calculate the adjusted RV coefficient between dx and dy, meaning that that quantifies the similarity between the two matrices that are, in this case, the triangular matrix of the distances between pairs of rows of X and the triangular matrix of the distance between pairs of rows of Y. That's so simply. And we get this result, and that's our Saturn coefficient. The result is a real value between 0 and 1, where 1 means perfect preservation and 0 means totally wrong preservation. That's so simple. And but then we had another problem, that is, how do we validate our results? How do we verify that our Saturn coefficient is informative, is useful? So we decided to check if the clusters found by HTB scan in the original data sets were preserved in the lower dimensional data sets. So we invented a new metric called HTB scanners that calculates this aspect, and we used it as a ground truth. For example, in this plot of artificial data, we had 3 clusters before applying UMAP that you can see on the left, and then the result after applying UMAP, you can see it on the right, and you can see that they were still 3. So 3 were before, 3 were afterwards, and so our HTB scanners was preserved. Basically, that was this was our process of validation. We took an original data set, we applied UMAP, we saved its results. Then we, on one side, we applied HTB scan on the UMAP output, on the UMAP layout, And on the other side, we calculated the Saturn coefficient, continuity, and trustworthiness. On the other hand, we applied the HDB scan to the original data set. We get the HDB scan results, and then we compared the HDB scan results on the original data set with the HDB scan results on the UMAP layout through this step, which is based on the adjusted rand index, only if the number of clusters was the same, of course, because if we had 7 on one side and 3 on the other side, that's not a good result. And then as a last step, we checked if these, if the metrics on the left were consistent with the adjusted rand index on the right. So if it was consistent, we said, okay, it's going to be, it's informative, it's concordant. If not, we say inconsistent trend. We applied our approach to 4 artificial data sets and to 15 real-world biomedical data sets of data from electronic health records, bioinformatics, single-cell RNA-seq. And our Saturn coefficient was most informative in most of them. So, for example, we started with that artificial plot on the left. We applied the UMAP dimensionality reduction, and we got this, and we applied a HDB scan to see which were the clusters maintained and what was the level of our Saturn coefficient that stated if the structure was maintained or not. We took this other synthetic data set that is way more complex, Chameleon, and we applied the UMAP, and then we applied HDB scan to see which clusters were maintained, and we calculated the Saturn score, the continuity and trustworthiness to see what was the result. So as you can see, it is 4 data sets that also I reported in the article. We had that Saturn and HDB scanners were close together. Continuity and trustworthiness were almost 0 all the time. So we were a bit surprised that in all these cases, continuity and trustworthiness were not so good. And then we performed also these tests on 15 biomedical tests, where on 11 out of them, Saturn and HDB scanners were concordant, where there was only 4 cases where continuity and trustworthiness were giving results that were closer to the HDB scanners and not closer to our Saturn coefficient. And we took these data sets from different types, so electronic records, microarray gene expression, single-cell RNA-seq, and also ECG, biosignals, and physiology data. So basically, in most of these tests, we saw that our Saturn coefficient outperformed continuity and trustworthiness in almost all the tests that we did. So on all the 4 artificial data sets, on 11 out of 15 biomedical data sets. And on the other hand, we saw that continuity and trustworthiness, even if they are the benchmark, the gold standard for this problem, they were always extremely low, like 0.001 or something like that. And they always somehow communicated that there was no preservation of global structure and local structure. And so if you want to know more about it, about this project, we published a paper in February in the PRJ Computer Science Journal. And also I released 2 packages. One was in R and one is in Python. And the R one is called the Saturn coefficient. The Python one is called Saturn score. Doing the R one was easy. Doing the Python one was more complicated. And so, but the paper is out, you can read it, and you can, if you want to use the Saturn coefficient for your own dimensionality reduction, of course, I invite you to do so. Okay, that's it for me, and thank you for the attention.
Question? So nowadays in machine learning community, so people sometimes prefer to directly work with high dimensional data. Because of this high dimensionality, we can generalize. Like reducing the dimension is a kind of classic topic for me. But how do you compare like this change of trend?
Well, I think that sometimes, especially with big data, maybe it's not everybody has high computational power to handle data sets with thousands of features and maybe 20 gigabytes of data sets. So doing a dimensionality reduction, I think, is useful first for a visual interpretation, but also for having less computational power and maybe saving some energy from the.
In terms of visualization, definitely this is the best way to go. But how about real data processing, the classification, or some other predictions? Can you use like UMAP or some extensions as pre-processing?
Yeah. I think that also, especially in clustering, the results can get better. And I didn't say it, but our Saturn coefficient can be also used for hyperparameter tuning, because the UMAP has two important hyperparameters, the number of neighbors and the minimal distance. So people need to try different values with a grid search. And we say, okay, why don't you use a Saturn coefficient? If you get the value close to 1, then you're done, you're fine.
Okay, so hi everyone, my name is Francesco, and today I will present you the talk Regret Minimization with Piecewise Linear Rewards, and this is a joint work with Matteo, Alberto, and Nicola. Okay, next one. Okay, so let me start with an introductory example in which we have a principal that wants to incentivize an agent to perform some task. Think, for example, to crowdsourcing platform, in which we have the platform that wants to incentivize a worker to perform some task by providing a payment, and by providing a sort of payment, and the agent then complete the task depending on the amount of money that the principal commits to pay the agent if the project is completed. So let me formalize a little bit this model in which we have the principal that commits to pay alpha if the project is completed. Then we have the agent here that selects the level of effort to put in the completion of the project. Here in this simple example, we have low effort or high effort. The level of effort is not observed by the principal, that only observes the final outcome. So if the project is not completed, we have that both the principal and the agent's utility are equal to 0. While when the agent exerts high effort, we have that with probability 1/2, the project is completed or not. So when the project is completed, we have that the principal utility is equal to 1 minus alpha, because alpha is a payment from the principal to the agent, while the agent's utility is equal to alpha minus C, where C is the cost that the agent incurs into to complete this project. Okay. So when the principal knows everything about the agent, so these probabilities here, the cost, it is possible to compute an optimal alpha, so a payment that maximizes the principal expected utility. And here, what I want to present you today, what I want to discuss with you today is a different perspective. So it is an online learning perspective in which the principal doesn't know anything about the agent and wants to learn an optimal payment alpha, so a utility maximizing payment alpha, by repeatedly interacting with the agent. So let me explain this online learning version of the problem. So we have a repeated interaction over multiple rounds. At each round, the principal commits to pay alpha t if the project is completed. Then the agent, again, chooses whether to exert high effort or low effort on the project. And then the principal only observes whether the project is successfully completed or not, and gains utility 1 minus alpha if the project is successfully completed. So when the payment alpha is sufficiently small and lies in this interval, we have that the agent selects low effort, and so the project is completed with probability 0, and so the principal expected utility, it is equal to 0 times 1 minus alpha, which is 0. Well, when the payment is larger and belongs to this interval here, we have that the project is completed with probability 1/2, and so we have that the principal expected utility is equal to 1/2 times 1 minus alpha, and is here in this function here. Okay, so what we try to do is try to, starting from this example, to find a much more general framework that we denote with bandit with monotone jumps. So in bandit with monotone jumps, the learner action space is the 0-1 interval, and this interval is partitioned in subintervals here, A1, A2, A3. So to each interval is associated a different probability distribution, and the expectations of this probability distribution are a monotone sequence. So here an increasing sequence, and that's why we name our framework monotone jumps. And we also have a linear function, L in this case, so actually a affine function to be precise. And the expected utility of the learner is the product of these two functions. Let me explain why we call this setting bandit with monotone jumps. So I explained to you before why we say monotone, and from this plot here should be clear why we use the word jumps, because if you look at the learner expected utility, we have in this picture two jump discontinuity, because we have the product of a piecewise constant function and a linear function. Okay, if we go back to the principal agent example, you can see that this indeed capture what we want from the problem, because we have the piecewise constant function, which was the probability with which the project was completed. That was equal to 0 in the first interval A1, and it was equal to 1/2 in the second interval, and the linear function that was equal to 1 minus alpha. Okay, so let me just explain why monotonicity is necessary in order to learn an optimal contract. The reason is quite simple. If you look at this example, you can see that in this example, monotonicity is not satisfied. The expectation in the first interval is 0, in the second interval is 1/2, and in the third interval is equal again to 0. So as you can see, the principal expected utility is greater than 0 only in a very small interval, and so this problem may be too difficult to learn. It may be too difficult to identify where this function is positive. So this is why we impose this monotonicity condition. Okay. Again, let me just explain how the learner environment interaction unfolds here. So also in this case, we have that the learner selects an action alpha t from the 0-1 interval, that is the set of action space. Then the environment samples a point xt according to the probability distribution associated to the interval A2 in this case, because alpha t belongs to A2. And then we have that the learner observes this xt and achieves utility that is equal to L evaluated at alpha t times xt. If we think to the previous example, so the principal agent example, we have that this problem indeed is generalizing what we had before. Okay, so what we want to do is to minimize the regret, which is the difference between the utility achieved by an algorithm that always selects an optimal alpha minus the expected utility associated to the execution of our algorithm. And what we assume here, we assume that the learner doesn't know anything about the environment, so the probability distribution, where these probability distribution are located, their expectation, and so on. And the only part that is known is this linear function. Again, this is well motivated by the problem that we were discussing before, because we don't know how the agent is going to react to our payment, but we only know this the linear functions on how much we are paying the the agent, but we don't know how the agent will react. So whether the agent will put high effort or low effort in the project. Okay, so let me just explain that this framework generalizes some other framework in economics, like linear contract design, that is essentially the one that I described you before, and also posted price auction with finitely many evaluations, and also some first price auction. So we have some problem in economics that have this piecewise linear reward and satisfy the monotonicity assumption that I was discussing with you before. Okay, so first approach in order to design a no-regret algorithm, so an algorithm that achieves sublinear regret, is the following one. So we can discretize the 0-1 interval with a grid of step epsilon and run an algorithm such as UCB1. It is quite easy that this approach achieves a T to the 2/3 regret upper bound. We can simply decompose the regret upper bound in this way. The first term is the error that we incur by discretizing. And thanks to the monotonicity, we can upper bound this quantity with epsilon. And the second term is the error, so the upper bound on the regret due to the fact that we are running an algorithm such as UCB1. And 1 over epsilon is the number of arms here. And so by setting epsilon to T to the minus 1/3, it is possible to show that we achieve a T to the 2/3 regret upper bound. So the question here was, can we do better? Can we achieve a square root of n times T regret upper bound? And so the answer is yes, spoiler. And so this is our algorithm. And our algorithm is divided into epochs. And at each epoch, J, we set a threshold parameter delta J equal to 2 to the minus J. And we run 2 different procedures. The first procedure is the find jumps procedure. The goal of this procedure is to identify jump discontinuity is proportional to delta J. So the idea is quite simple. So for each interval I that belongs to capital I, we sample 1 over delta J square. We take 1 over delta J square samples from the extremes of this interval. Then we compute to estimate of the means at the extremes of this interval. And if the difference between these two quantities, so the difference between these two expectations is larger than this threshold parameter delta J, we halve this interval and we execute a recursive binary search procedure by looking for jump discontinuities proportional to delta J in these new 2 intervals. Otherwise, if this condition is not satisfied, we stop the binary search procedure. This is because maybe the jump discontinuity with this interval is too small, and so we need a smaller delta J in order to identify this jump discontinuity, or there could be no jump discontinuities within this interval. And the second procedure that we run in order to achieve the square root of n times T regret is this one. So for each interval, we shrink the interval by removing the subinterval whose expected utility is guaranteed to be suboptimal. And this is done by computing an optimistic estimate of the learner expected utility in that interval, and we remove the subinterval that is guaranteed to have suboptimal utility. And the reason is optimistic because, again, we use a sort of an upper bound on the leader utility, on the principle, the learner utility, to remove subintervals that are suboptimal. Okay, this is an high-level idea of our algorithm. And what we can prove is that we can indeed achieve a square root of n times T regret upper bound. And when n is sufficiently small compared to the time horizon, we have that this regret is tight. Okay, so just to briefly mention that this improves a regret upper bound in linear contracts by zoo. And it also improves results by Nicolò and this group in posted price auctions with infinitely many valuations. Okay, so just to mention some future directions. The first future direction here, the problem is fully stochastic, but we consider in principle, we could consider in principle adversarial settings. And another future direction is to find an algorithm that works for, in general, not only for piecewise linear function, but also for general one-sided Lipschitz function, for example. So thank you very much for your attention, and this is it.
Questions?
Yeah, I was going to ask you, but you made the reference. Yeah, you were looking at that paper there. So yeah, talking about adversarial, what are, so can you, are there trivial lower bounds that show you that you cannot do it adversarially? You can switch on that mic. Switch on that mic. Just push there. Yes. Don't be so close. Don't be so close. Okay. Yeah. So what do you envision some fundamental lower bounds that prevent adversarial? Have you thought about that?
Yeah, I think that this approach for sure doesn't work because this is an approach based on identify jumps discontinuity. But when we have adversarial problem, this doesn't work anymore. And the idea probably should be the one of using a variance-aware approach of the zooming applied to here, but we are still working on here and on this topic, and so we don't.
Yeah. So because the utility here you have you do have Lipschitzness in one direction.
Yeah.
So you can still use discretization.
Yeah. But in that case, I think that you achieve a T to the 2/3 regret upper bound if you.
Nope. See, if you have this. Oh, I see. Because there is no.
You want a kind of square root of number of bias.
No. Yeah. You need some other properties. Okay, but it's cool. I mean, many times you need some additional maybe property like smoothing the adversary.
Yeah.
So that it cannot pinpoint the jumps perfectly, but it's a nice problem. Yeah.
Thanks for great talk. And in your model, L is assumed to be linear function, right?
Yeah.
So, and your one open question about Lipschitz is just generalize L to nonlinear function.
Yeah, I think that the point is that L is known. So as long as it is known, I think you can also work with the Lipschitz function. But I think that at the moment, the most probably interesting thing is to consider cases in which L is not known. The fact that L is known is well motivated by pricing and also contract example, because that function is how much you are paying an agent. And so this is why we assume that this quantity is known. But yeah, I think that probably the most interesting direction is to assume that L is, to relax the fact that we know the function L.
I see. Okay. Thank you.
Thank you.
Thank you. I want to ask you if there is, if you think that your method can be applied to any case in which you have like this kind of piecewise linear functions, or if it's somehow binded to the kind of feedback that you imposed on a problem. So the fact that it generates starting from this I don't know, you have a figure on it, but it starts essentially from this piecewise constant stuff, and then you have a loss function. Yes, to that one. That okay. Yes. If you think that your method can hold, if you can be applied if you start from the third figure by neglecting the first two.
That's a good question, because in the analysis we use the knowledge of this function L that we assume to be known. So yeah, at the moment I don't think that this approach exactly works, but it is for sure an interesting direction to relax the fact that you know L and you start directly working on this function here.
Okay, sorry. And you start directly from this function here, because when you know L, you can somewhat decompose the problem with these two quantities. So at the moment, I don't think that our algorithm can handle this case because we explicitly use the function L. But yeah, it is for sure an interesting direction. So thanks for the question.
Okay, thank you very much.
I'm Marco Braga from the University of Milano Bicocca, and today I will talk about task arithmetic for contextualizing language models. So here just a bit of background. So large language model are usually pre-trained on a large amount of unlabeled text and data. And then these models are trained to generate a text by predicting each token. So a sequence of token. Generally, the knowledge is stored implicit in the parameters of the large language model. And this knowledge is then difficult to update. Then at inference time, we can ask to the language model to solve some specific problem or some specific task in a specific context with a prompt, so describing what we want or what we expect to be the output of the model. So we start from an observation that large language models are powerful, but their knowledge is frozen in the weight. So if the models are trained when the Pope was Francis, then the model will not know that now the Pope is Lion. This is just one example. So the question is, do we still need to adapt this huge billions language model? And the answer is briefly yes, for two main reasons. So the first one is that when we use the prompt, seems to work well, but even small changes in prompt can strongly affect the final performance of the model. So, for example, in a paper published in ECLR 2024, Sklar shows that in a classification task, the accuracy can vary from 0.2 to 0.8 by changing only the punctuation in the prompt. The second reason is that recent work published at Loic Calling shows that fine-tuning, so training small models can outperform large language models if we use in a zero-shot way. But the problem is that if we fine-tune this model, this is a process that is expensive because it needs a lot of GPUs, a lot of labeled data. And for example, if we are focusing on different domains, we need one model fine-tuned for each domain or task. So our question is, how can we adapt a large language model to specific task or domain in an efficient way? Here, I will just do a brief summary definition of domain and task, which of course are related, but there are some differences. So if we consider domain adaptation, a domain can be, for example, legal domain, biomedical domain, or scientific domain. And the main issues there is that we can have different language style or terminologies or language distribution. And usually we have a lot of unlabeled text. For example, we have a lot of legal documents, a lot of laws, for example, but they are unlabeled. The task is a bit different because we are asking a model to solve a specific problem. So we can have, for example, question answering or summarization or classification. And usually the task adaptation requires label data because we need to some label to learn how to, for example, classify a text. So what is the key challenge? That we have a lot of unlabeled domain-specific data, like as I was telling you, laws or medical papers, for example, but then we don't have a lot of task-specific labeled data, because this requires annotation by expert, and usually you have to pay a lot, and it's also time-consuming. Here, the question is where does the knowledge live into the parameter of the large language model? So we have two possibilities: the parametric knowledge, which is the one that is internal to the model, and it's a lot difficult to update. And if you, for example, try to further fine-tune a model on a new task, maybe there will also a problem of forgetting the previous knowledge. And then we have the external one, which is usually stored in a database, and it's more explicit, and you can also update this knowledge with new information. So the question is how we can combine this internal knowledge with some external knowledge in an efficient way. Recently, in 2023, Hilario et al. Proposed task vectors in a paper published in ECLR. So the idea, I think it's quite easy. We can consider a pre-trained large language model, which is defined by weights theta 0. Then we can consider the same model fine-tuned on a specific task or on a specific domain, which is theta t. And then we can just take the difference of theta t and theta 0 of the weight of the models. And this one is defined as the task vector tau t. This task vector represents the knowledge that the model has learned during the fine-tuning process. So the knowledge that the model has learned to solve a specific task or to be good in a specific domain. And then when we have this task vector, we can combine them by simply arithmetic operation like sum, or if we want to subtract some task vector. So here there is an example, an image. For example, if we have a specific domain, which is medical domain, then we have a specific task, which is question answering. And we start from a model theta 0, a large language model. Then we can fine-tune this model on a question answering task. We can see general purpose, so which is not domain specific. And we can obtain the model theta t, for example. Then we can fine-tune the same model theta 0 as a mask language model, so on an unlabeled data on a medical domain, and we will obtain theta d. And then we can just sum the task vector of the domain to the model theta t to obtain a new model, which will be able to solve question answering tasks in the specific domain, so in the medical domain. Why task vectors are useful? So the hypothesis that is behind task vector is that fine-tuning behaves like a gradient flow in a shared weight space. So the task or the domain correspond to a specific direction in the weight space. So even if the path is not linear, then we can consider like as a linear path from the origin to the specific model, the model fine-tune a specific domain or task. And so task vector approximate this direction of adaptation in the weight space, and we can sum up them as vectors in the space. So here, just a brief summary. So full fine-tuning is still required, but it requires a lot of computational and time resources, and then we need a large amount of labeled dataset. For this reason, we focus on task arithmetic, which can be useful to inject the domain or task knowledge via simple arithmetic operation. And we don't need label data, so task-specific, domain-specific label data. We can apply it in a zero-shot scenario, and we don't require any further training. I will show a few special cases regarding task vector, specifically in information retrieval, since our lab and me, we focus on information retrieval. So information retrieval is a specific subfield of NLP and AI, which aims to retrieve a relevant documents from a huge database of documents, given a user query written usually in natural language. So it can be some keywords or a sentence, for example. Usually the pipeline for information retrieval is taking a large language model, fine-tuning it on MS-Marco, which is a huge collection of documents and query. But MS-Marco is it's a huge label collection, but the problem is that MS-Marco is not domain specific. So we can say that it's like a general purpose dataset. The problem is that sometimes we need to do information retrieval on specific domains, like scientific or biomedical one, or even in different languages. Here there is, for example, Spanish. And one of the most popular approach is to apply a model fine-tune on MS-Marco in a zero-shot way to different domain. But of course, sometimes this is not enough. But why this is the most popular approach? Because having labeled data for information retrieval is quite expensive, because you need a lot of experts that classify all the documents if they are relevant or not with respect to a query. So for this reason, we, and inspired by task arithmetic, we decided to apply task arithmetic in information retrieval. Here there is an example of a summary of the approach. So we start from what we call a base information retrieval model, which is a model fine-tuned on MS-Marco. Then we consider a domain model, which is the same architecture, so the same model, which is fine-tuned as a mask language model, so just to learn the language distribution on a specific domain. And this domain can be legal domain, biomedical, financial domain. We compute the task vector between the domain model and the pre-trained model, and then we sum up this task vector to the base information retrieval model to obtain a domain-specific information retrieval model. This approach is published in last year CIGIR, and what I think is also interesting is that we use all publicly available fine-tuned models. So basically in our paper, we don't train. And in this way, we can, of course, avoid using labeled data, but also save a lot of GPU resources. Here I report some results in domain-specific collection. So here I report 4 datasets with focus on biomedical and scientific information retrieval. NF Corpus, for example, is a question answering dataset in which the questions are written by, we can say, non-expert. So the language is easy to understand, while the documents are scientific papers, so there is a lot of technical and domain-specific language. Track COVID focus on question about COVID-19. While, for example, SciFact is for scientific fact-checking, and SciDocs is citation prediction. So we have papers, we have the title of the papers, and we have to understand if a paper is citing another paper or not. I report the results with Mono T5, which is a T5 model fine-tuned for information retrieval, and the same for Roberta, which is a BERT-based model. And the application of task vector, which we call TV, outperforms the information retrieval models on 3 out of 4 scientific dataset. Then we have also some results for multi-language information retrieval. So in this case, we start from a model, a multi-language model, which is multilingual T5. And then the model is fine-tuned on a MS Marco, so the approach is the same as before. And then we sum up a task vector, which is now more related to a domain, but which is related to a specific language, and in particular, Spanish, French, English, and German. And we can see that the application of task vector significantly outperform the information retrieval model on all the proposed languages. Last, I will show another possible approach of task vector. In this case, the aim is not to adapt a model on a specific domain or task, but the idea is to try to understand what the model is learning during fine-tuning. So that's why I called it task vector for model interpretability. In this paper, which was published at ECIR this year, we focus on Mono T5. So just briefly, Mono T5 is a T5 version fine-tuned for information retrieval, and the model receives usually a structure input, which is query, and then the query, document, then the document, and then like a question, so relevant if the document is relevant to the query or not. And then the model will generate yes or no. Sorry, true and false if the document is relevant to the query or not. So the question is, which parameter change more while fine-tuning Mono T5? So while fine-tuning T5 on a specific information retrieval task. Here we report the results with the maximum distance, just because this does not depend on the dimension of the layers and of the especially the embedding layers, which are a bit huge compared to the other attention and dense layer of the transformer model. And we can see that the changing, so the fine-tuning process is dominated by changing in the embedding layers, while there is a minimal adaptation for attention and dense layers. So for this reason, we decided to focus on the embedding layers, and we can see also that the maximum distances between the T5 base and the T5 fine-tuned for information retrieval are in these specific token embeddings, so document, query, relevant, true, and false, which are the tokens that I showed you before are in the structure input of the model. So what we can understand is that a lot of knowledge that is learned by the model is like injected in these specific token embeddings, basically because these tokens and these embeddings are trained to address a task-specific instruction. So what we proposed was a new version of T5 where we trained only that 6 embeddings. So the embeddings of query, document, relevant, the end of sentence token, and also true and false. This approach is much faster compared to full fine-tuning because we just updated 6 embeddings layer. And we also evaluated on these are the same dataset as before, so on both in-domain and out-of-domain dataset. And we can see that our approach that we called light mono T5 achieve statistical equivalence compared to the full fine-tuned model, which is mono T5, on 3/4 dataset. So just to conclude, I presented task arithmetic, which is a training-free approach, a zero-shot approach for model editing through simple task vector operation. And then I showed how we apply this approach to information retrieval. In the first paper, we applied task vector for improving domain-specific and language-specific models without further fine-tuning, so we don't need neither training, neither the label dataset. And then we also showed how task vector can be used to support the interpretability of specific large language model in the field of information retrievals. And the takeaway is that task arithmetic show that fine-tuning trajectories have some geometric structure, and so that we can take the task vector, sum up them as vector, and we can use model or use task vector to define new model without further training or dataset. Thank you. If you have any question, I'm here.
Questions from online learning people? It would be nice to see some relation between online learning research and fine-tuning and in LLMs. These are essentially the same problem.
Yeah.
What's the typical gap so far? In the case of prompting is one of the current trends.
Yeah.
Still we can fine-tune the model,
yeah,
or maybe output layers.
Yeah, exactly. Only few layers, only few parameters, for example.
So if
Yeah.
you focus on the final output layer, it is essentially a linear predictor.
Mhm.
Then can we apply some standard online learning technique in some way? So theoretical analysis is not exactly the same, but some tastes could be transferred to the real world problem. That was my feeling. Any questions or comments? We need food to discuss. Okay, then let's continue the discussion over lunch. So thank you very much.
Thank you.